All right, so lesson 43 is more practice with U-substitutions. So we're going to do a little bit more, so hopefully you guys get more familiar with these. So remember I told you they're super important, so we have to practice, practice, practice. And unfortunately in math, a lot of times practice, practice, practice means you have a lot of problems to do. So number one, so I have x squared minus 16 raised to the fourth times 2x dx. So Anne texted me last night and she said, how do you know, like on the instructions it said, sometimes you can use U-substitutions, but if it's easier to not use it, then don't. So she was like, well, how do I know which ones are easier to not use the U-substitutions on? If this had been something like a squared power, I would probably just go ahead and FOIL it out and then do the antiderivative that way. But if it's raised to the fourth, not very fun to multiply it out 4 times. Does that make sense? So if it's just like squared or something, just FOIL it out. Not a big deal. If it's raised to the 24th, please use U-substitutions. That would be miserable to multiply something out 24 times. You understand what I'm saying? Okay, so this is why we have to learn this rule. So we're going to let our u be x squared minus 16, and our du then is going to be 2x dx. So as we look at our problems, it's just like the chain rule. It's like if you were taking the derivative, where would you need a chain with the derivative? You would need it for the inside part, the x squared minus 16, right? So that's why it's our u. So we're going to have u to the fourth, and then the 2x dx is replaced by the du. So we're going to have u to the fourth du. So everything, there are no x's left in this problem. That's what we want. We want to change everything to u's. So now when I do the integration, I'm going to have u to the fifth with a 1/5 out front plus c. So your final answer should be 1/5 times x squared minus 16 to the fifth plus c. So we resubstitute. So we had u is equal to x squared minus 16. We replace that u with x squared minus 16. Yeah, Sydney. I could have done 1/2 du, but see how in the problem I have 2x dx? That's what I'm trying to eliminate. Like up here, I have 2x dx. So if I can replace it with all of du, then that's fine. So you don't have to always do 1/2 du equals x dx, right? So this next one, so I'm going to let my u be the 1 minus 3x squared. Du is then negative 6x dx. So notice how that's what I want. I want that negative 6x dx. So all of that is going to be replaced with du. Now the other part is going to be u under a cube root, so this is going to be replaced with u to the 1/3. So we rewrite, so we have u to the 1/3 du, and then we integrate. So we add 1 to the power, we do the reciprocal out front, so 3/4 u to the 4/3 plus c. So we end up getting 3/4. Our u was 1 minus 3x squared to the 4/3 plus c. Done. Okay, so what do we think our u is on the next one? T to the fourth plus 5. So if I let u be t to the fourth plus 5 and I take the derivative, now I have 4t cubed dt. And that's where we don't really want a 4, right? We had t cubed dt here. So if I want to get t cubed dt, then I divide the 4 over. So I would have 1/4 du. So that's what Sydney was asking about. She's like, sometimes you divide that 4 over, like sometimes you leave it. Why is that? Do you guys get it? So when we replace, we're going to have the square root part was the square root of u, and the t cubed dt is now replaced with 1/4 du. So the 1/4 we can just kind of pull all the way to the front. It's just a constant being multiplied, right? So this is the same as 1/4 the integral of u to the 1/2 du. So I have 1/4, and when I integrate u to the 1/2, I get u to the 3/2.
Where did dt go? You know who it was like 2 to the 3rd dt?
Well, the dt is replaced with a du term as well. So the dt, this t cubed dt, was replaced with what it was equal to, which was 1/4 du. That's all replaced there. All right, so we end up getting 2/12, which is 1/6. Yeah, Isbeth? I took the derivative of u, so the derivative of t to the fourth plus 5 is 4t cubed. Like if I had x to the fourth, its derivative is 4x cubed. That's what I was doing. All right, and then I plug in my t to the fourth plus 5, my u. That is your answer. Okay, so next one. What do you guys think u is? 1 plus r to the fourth, exactly. Our du then is the derivative of that, so it's going to be 4r cubed dr. We look at our problem and we're like, oh, I don't have a 4 with it. I just have r cubed dr. So I'm going to write it as 1/4 du equals r cubed dr. So when we replace, the bottom is u squared. The r cubed dr is replaced with 1/4 du. So we can write 1 over u squared du, which is really our u to the -2 du. Now, a lot of you guys are messing up integrating with negative exponents. If you have u to the -2 and you add 1 to the power, you're not at u to the -3. You add 1 to the power, what are you at? U to the -1, right? And then we have a 1 over -1 out front, so still -1. And then times our 1/4 plus c. So we get a -1/4, and then times u to the -1. So you can write parentheses 1 plus r to the fourth raised to the -1, or you can write it as 1 over 1 plus r to the fourth, either way, plus c. And that's our answer. Running out of room here. Okay, is this making sense? So what do you guys think for number 5? How would I do the setup? What's
so
my...
like d to u is 1 plus x to the fourth.
And then what's du? So the derivative of that?
4x to the third, and then you do 1/4.
Exactly. So now when you replace, the x cubed dx is being replaced with 1/4 du. And then our over, that we have the square root of 1 plus x to the fourth. Well, that's going to be 1 over the square root of u, which I'm going to write as u to the -1/2. Do you guys understand that?
1/4 times 1 over the square root of u.
Exactly. So when you have 1 over the square root of u, you can write that as u to the -1/2. So now when we integrate, we add 1 to the power. So I'm going to get u to the positive 1 over 2. Its reciprocal of that power is 2 plus c. So I get 1/2. U to the 1/2 is going to be 1 plus x to the fourth raised to the 1/2 plus c. Or just the square root, right? You could write the square root instead of the 1/2 power. Does that make sense? You guys get it? Feeling better with this? All right, so the next one, I wouldn't do a U substitution on. You don't have to. If you don't have to do a U substitution, just use our power rule, right? That's easier. So on this next one, I would rewrite. Now on the test, though, a lot of you guys messed up with your numbers, your coefficients. So like on this first one, when I rewrite, it's 1/3 x to the third, right? And the next one is 1/4 x to the -2. Some of you guys were sneaking the 4 like up on the numerator and writing it as 4x to the -2. That's not what it is, right? 1/4 x to the -2. And so we don't need a U substitution. So it's just like with derivatives. You have to know the method. You have to know, do I use quotient rule, product rule, chain rule? When am I using what? Sometimes you use U substitutions, sometimes you don't. We're going to learn lots of other methods for integration. So you got to know the difference between them. So when I integrate this one, I'm going to do 1/3. I'm going to have my x to the fourth with a 1/4. I'm going to have x to the -1 with a -1. And I still have my 1/4 as well. Plus c. So your final answer should be 1/12 x to the fourth minus 1/4, and I can say times 1/x, but where else could I just put the x? Down with a 4, right? Oops, that got a little crazy.
Where'd you get the 1/3 times 1/4?
When I was integrating, I added 1 to the power, and then did 1/4 out front, right? If I'm integrating x cubed, right? All right, and that's our answer. so know when you use it, know when you don't. All right, ready for the next one? All right, so do I need a U-substitution? Do I not need a U-substitution? You do not. Okay, and this is actually leading to something like we do volume formulas with, this is called the shell method that this is set up as. But anyway, so we would do the 2 pi is just a number. We can pull that out. And then we have x multiplied by 9 minus x to the 3 over 2. So let's simplify that first. So it's going to be 9x minus, what do you get when you do x times x to the 3 over 2? Yeah, you get common denominators and add the exponents, right? So it's x to the 5 over 2. So the 2 pi is just a number. We keep it out there. And then we're going to integrate the rest of it. So I'm going to have 9 times 1/2 x squared, or 9 over 2x squared, minus, I add 1 to the power, so instead of 5 over 2, I'm going to have 7 over 2. So x to the 7 over 2 with a 2/7 out front, right? So I'm going to have my 2 pi times 9 over 2 x squared minus 7 over 2 x to the 7 over 2. And you can leave it like that, or you could multiply the 2 pi n. 2 over 7, what, oh, did I switch it? 7 over 2, yeah. Thank you, Valerie got me. 2 over 7, thank you. So that's our answer. So you can leave it like that, or you can multiply the 2 pi n if you want to. All right, so now for the secants, tangents, sines, cosines, all of those. These are the tricky ones. It's hard sometimes. Sometimes you write down a u and you're like, ooh, this u didn't work. And try something else. Yeah, Charles?
Plus C after.
Thank you, plus C. Should I give him one for the plus C? You know how many times I don't count you off for forgetting the plus C? I think I should be given a freebie for that one, huh? We'll see. All right, so the next one. So what do we think? So we have tangent and secant squared. U equals tangent, right? And it kind of makes sense because it's under that square root again. So we like when there's kind of that little, I don't know, red flag, I guess. It's like you can see what it's going to be. So when we replace, we do have the square root of u du, which was u to the 1/2 du. So when I integrate, I get u to the 3 over 2 with the 2/3 out front plus c.
What about the
Yeah, the secant squared x dx was replaced with du, yeah. And then our u is tangent, so it's going to be tangent of u to the 3 over 2 plus c. And if this was a multiple choice question, it could be written lots of funny ways. You could have like the square root of tangent cubed, right? Those are all equivalent, you know, the different ways to write this. Oh, dang it. Tangent of x. Man, you guys are just really going to get some bonus points here. All right, so that's our answer. All right, so think about the next one. What do you think u is? Yeah, it's just x over 2. So du, don't do like quotient rule or anything. That's the same as 1/2 x, right? So its derivative is 1/2. So now when we replace, we have cosecant squared of u, and then the dx is replaced by 2 du.
You don't have to replace the cosecant squared.
No, because that wasn't part of our u, right? So
Like-
then, yeah,
On like the last one, like secant wasn't.
it depends on what you're letting your u be. So like secant squared x dx was part of that derivative, right? We don't have a cosecant as part of our derivative this time, so it's not replacing that. All right, so cosecant squared u. You know how to take the derivative of something to get negative cosecant. So remember on your derivatives drills, what gave you a negative cosecant squared? It was cotangent. So if I want this to be a positive cosecant squared, it's negative cotangent. So this is negative 2 cotangent of u plus c, which is negative 2 cotangent of x over 2 plus c. Okay, thoughts on the next one? Are you guys getting to the point where you can see it? Pi minus x. Because then du is just negative dx. And this all becomes something that we can take the derivative of something to get this, right? What do we take the derivative of? Sorry, I left off the negative du equals dx. So what do I take the derivative of in order to get secant x tangent x? I take the derivative of secant, right? Yeah, exactly. Charles is good with his derivative drills. Are the rest of you good with your derivative drills? All right, that's our answer. Yeah, the negative came from the derivative of pi minus x was negative dx.
Oh, yeah.
Yeah, you see it. All right, so we got a few more, but now these have numbers. These are definite integrals.
So it's not secant squared?
No, because secant squared, if that was our y value, its derivative would involve a chain rule. It would be 2 secant x times secant x tangent x, right? But if I just have secant of x, its derivative is just secant x tangent x. So you're going backwards, antiderivatives. You have to know your derivatives. I really feel like calculus is like 65, 70% memorization. You have to memorize every single thing. And I always say, like, in U.S. history, Mr. Bradley asked you to memorize an insane amount of information. And you know what? People do. Like, people memorize it. People that I would never expect to get a 5 on the U.S. history test will get a 5. And I'm like, wow, never would have thought that. But they memorize all that stuff. But then in AP Calc, I'm like, memorize this. And people are like, meh, I'm good. I'm good to memorize it. Memorize everything, okay? All right, so number 11. So I have the integral from 1 to 5 of x over the square root of 2x minus 1 dx. This is a tricky one. Because now this is one where when I let my u be 2x minus 1, which is what it should be, my du only becomes 2 dx. Yeah, so we need that x dx, right? We're trying to replace x dx. So this is one of those problems where we have to solve for x. So we take our u equation and we add 1 to it, and we divide by 2, and we get x.
Can we do 1/2 x du?
Yeah, you could, 1/2, hang on.
Could we have an x as another constant out in front?
1/2 x du. I don't know what you're saying.
Because isn't the du right now technically in the problem, isn't it like x dx? So don't we need something to be able to...
Yeah, we need to replace that x. That's what I'm saying, yeah. So that's why we're solving for x. It's one of those ones where you have to get it by itself. 1/2 x du. I don't know what you're saying. All right, so, yeah.
Okay, so number 9, so we didn't need to replace cosecant squared because it wasn't a part of the derivative. You know, like it wasn't a part.
Uh-huh.
But x isn't a part of the derivative here, so why do you need to replace it?
Because we need to have everything in terms of u. So like when we wrote this, everything had u in it. We can't have x's and u's. That's weird. Substitution didn't work if we have both variables, right? We're trying to substitute to a new variable. So everything has to be switched to u's. So when I do this, my x dx, my x is replaced with u plus 1 over 2. My bottom part is the square root of u. My dx is replaced with 1/2 du. So it looks kind of messy for a second, but we're going to clean it up. So think about it. If I have u plus 1 over 2, you don't have to write this, divided by the square root of u, doesn't that become times 1 over u? Right? Does that make sense? So when we rewrite, I'm going to have my 1/2, and then I have my u plus 1 over 2, and then times 1 over u, so that u to the 1/2 is on the bottom still.
So you got 2 plus 1 over 2 because you just did like u plus 1 over 2 times.
I just solved for x. I got the x by itself, so I added the 1 over, and I divided by 2.
No, I know. I mean, like on the if you do u plus 1 over 2 times
So that's replacing that x.
Or whatever.
Yeah, you see it.
I know. But I'm saying the
Okay,
next step.
I'll
Like,
answer
how
after class, hang on. So I have 1/4, and I'm going to have u plus 1 over u to the 1/2. So we continue to simplify, so we're like, okay, I got 1/4. I'm going to have u to the 1/2 plus u to the negative 1/2. So I'm just simplifying by bringing this u to the 1/2 into both pieces of the numerator. And now we integrate.
And then, I'm sorry, where did you get the 1/4 from?
I'll show you this one all over again. Hang on. Yeah, we're definitely running out of space, right? You can go to 12 because we'll skip it. We'll skip 12. So this ends up being 2/12, so 1/6, u to the 3/2. Well, what was u? It was 2x minus 1 to the 3/2 plus 2 times u, which was 2x minus 1. Oh, so I have 2/4 actually. I'm going to write that as 1/2. Forgot my 1/4 out front. So 2/4 is 1/2. X to the, so 2x minus 1 to the 1/2 plus c. So I just distributed this 1/4 into both things. Oh yeah, we are doing numbers, aren't we? I forgot. Definite integral. So at the very end, instead of plus c, now we're just going to plug in, what is it? 1 and 5. So you can do this one of two ways. Remember the two ways I showed you yesterday? You can keep everything as x's and go back to x's at the very end, or you can change things to u's. So if you guys changed to u's, that's fine. So that if you were here, then you would have u values from something to something. Since I already went back to x's, we'll keep it. So if I have 9, let's see, 2 times 5 was 10, minus 1 is 9. So what do I get when I do 9 to the 3/2? 27. So I have 1/6 times 27 plus 1/2 times, this was 9 to the 1/2, so 3. And then minus 1/6 times 2 minus 1 is 1. To the 3/2 is still 1. Plus 1/2, 2 minus 1 was still 1. So that's still 1. So I have, leave it as 27/6 plus 3/2, because see how you also have a 1/6 over here and a 1/2. So 27/6 minus 1/6 is going to be 26/6, which is 13/3. And then 3/2 minus 1/2 is going to be plus 2/2, which is 1. So you should get 16/3 as your answer. All right, so the next one's just like it. It's number 12. That's just like that. So let's skip to the next two. Okay, good. Do you have that all copied down? All right, so this one. So I have the integral from 0 to 1 of x times the square root of 1 minus x squared. So again, your u is 1 minus x squared. Du becomes negative 2x dx. So I get negative 1/2 du equals x dx. Okay, x dx was there. So when I replace, I'm going to have my negative 1/2 in the du, or replacing the x dx. And then the square root of 1 minus x squared, that's our u to the 1/2, right? The square root of u. Now let's do the thing where we actually change our numbers to u's. So if I have u of 1 and u of 0, we want to know what those change to. So looking at our u equation, plug in 1 and plug in 0. What do we get? When I plug in 1, I get 0. When I plug in 0, I get 1. So instead of going from x equals 0 up to x equals 1, I'm going to start with u equals 1 to u equals 0. So if that bothers you that they're upside down, basically, remember what you can do? You could flip it and make it the opposite sign. So instead of having negative 1/2, I could make that 1/2 from 1 to 0, or not 1 to 0, 0 to 1. So u to the 1/2 du, up to you guys. So then I get u to the 3/2 with a 2/3 out front and my 1/2 from before. It was, but I flipped it. So then my 2's cancel, so I get 1/3, and then I have u to the 3/2, so 1 to the 3/2 is 1, 0 to the 3/2 is 0, so my answer is 1/3. very last one, do I need a U-substitution? Just if that bothers you that it goes from a number that's big here and to a smaller number there. Like we don't typically see that, we do 0 to 1. So you can flip it and make it the opposite. Yeah. I mean, you can keep it how it is. You're just going to have the 0 part first and then minus the 1 answer, right? And then that's going to be the opposite of what you have anyway. So either way. All right, and the very last one does not use the U-substitution. Do you guys see it? Can you integrate x? Yep. Can you integrate cosine of x? Yep. So it's really just kind of breaking apart the integral. So we're integrating x, and we have 1/2 x squared, and that's going to go from pi over 3 to pi over 2. And then integrating cosine, what do we get? Sine or negative sine? Sine, right? So pi over 3 to pi over 2. I do expect you to remember your unit circle. I know you guys are totally pros at this, right? And then we're going to subtract out the other one, so 1/2 pi over 3 squared plus sine of pi over 3.
Is it not 1?
So we get 1/2 times pi squared over 4 plus, what is sine of pi over 2? 1, because I took the antiderivative of x and got 1/2 x squared. All right, and then I have minus 1/2 times pi squared over 9, and then sine of pi over 3. What is it? Root 3 over 2, good. So we're going to do minus because I distributed my negative, so minus root 3 over 2. Lovely answer. I'm just going to leave it like that. We'll call it a day. All right, so is this making more sense?